Hey everyone, welcome to The Explainer. So today we're tackling a massive challenge that pretty much every tech team is sweating over right now. The massive jump from building a cool AI prototype to actually running a production-grade enterprise system. It's incredibly common to build this AI toy prototype that looks like absolute magic in a controlled demo, only to realize that deploying it in the wild is a completely different, highly rigorous reality. Building a true enterprise-grade AI system requires some fundamental shifts in how we think about architecture, scale, and safety. Okay, let's dive right into this. We've laid out a roadmap with 6 foundational pillars to help mature your AI architecture today. We're going to cover taming multi-agent chaos, scaling for 10x growth, navigating the build versus buy trap, ensuring high-stakes reliability, designing for ethical AI, and finally, architecting for the future. All right, let's kick things off with pillar number 1, taming multi-agent chaos, or how we move from wild autonomy to actual governance. You know, multi-agent systems are absolutely incredible, but without the right boundaries, they can easily devolve into complete contradictory chaos. In the toy phase of AI development, you see this anti-pattern all the time. Autonomous agents basically racing against each other. They have overlapping jobs and totally fragmented context. It's like having a research agent and a response agent trying to answer the exact same factual question using completely different context and ending up fighting like toddlers over a toy. But in the real world, the production reality, you need explicit role boundaries, central orchestrators calling the shots, and shared state layers. Every agent has to work from the exact same established facts. So the absolutely crucial point here is this. Multi-agent systems need governance, not autonomy. Now, I know the whole magic of AI agents is the idea of letting them just figure it out on their own, right? But autonomous agents without coordination, they just become contradictory agents. In a mature architecture, the coordination between those agents matters vastly more than the individual intelligence of any single agent. To actually enforce that governance, you need a highly explicit architecture with super strict input and output contracts. Think of it like an assembly line. The retriever finds the information, the reasoner analyzes it, the verifier checks the factual accuracy, and finally, the responder generates the output. And here's the kicker. They never overlap. The retriever doesn't reason, and the reasoner definitely doesn't retrieve. By enforcing these strict boundaries, you keep agents from stepping on each other's toes, and any contradictions become instantly detectable. Moving right along to pillar number 2, scaling for 10x growth. This is all about efficiency and sustainable expansion. Because let's be real, when your user base suddenly explodes, simply throwing more money at GPUs is going to bankrupt you. You need smart architectural shifts. Look at the inference layer. You've got to move away from relying on one single, massive, expensive model and switch to a routing layer that uses specialized models and semantic caching for repeated queries. Over in the retrieval layer, instead of running a full, heavy retrieval every single time, you switch to tiered retrieval. Filter cheaply first, then do the expensive similarity searches. And for your data layer, drop the synchronous writes. Shift to a CQRS pattern where you optimize asynchronous read and write paths completely independently. Now, deep breath, you don't have to build all of this overnight. Here's a very realistic 12-month roadmap. In phase 1, so the first 3 months, you just focus on quick wins, things like caching and response streaming. That alone gives you 2 to 3 times more throughput right out of the gate. Phase 2, months 3 to 6, is when you horizontally scale using containers and load balancing. And then finally, in phase 3, you tackle the really deep architectural optimizations like model routing. If you face it correctly like this, hitting 10x scale should really only bump your infrastructure costs by about 3 to 4x. Why? Because your system is actually getting vastly more efficient as it grows. And speaking of efficiency, check out this massive metric, 80%. Just by implementing a model routing layer that pushes simple tasks to smaller, specialized models, instead of waking up your massive single model every time, you can snag up to an 80% cost savings. I mean, that is just incredible architectural leverage. That's how you keep a growing business totally sustainable. Okay, pillar number 3, the build versus buy trap, prioritizing strategic fit over our own technical pride. This honestly addresses one of the most emotional choices an AI architect has to make. Look, as engineers, our natural instinct is to build literally everything from scratch because, well, we want total control. But we have to balance that against strategic business reality. You have to step back and ask, is this component a true source of competitive advantage, or is it just enabling infrastructure? If it's your unique moat, absolutely, you build it. But if it's infrastructure, like a vector database, buy it. Modern vector databases handle billions of vectors with sub-10 millisecond latency. Unless you are literally selling a search platform as your core product, do not waste time reinventing solved problems. And if your team is really pushing hard to build a custom solution anyway, keep this golden total cost of ownership rule of thumb in your back pocket: 3x. If your internal estimate to build the thing is within 3x of a vendor's price to just buy it, you are vastly underestimating the build. Because you aren't just paying for the initial code, right? You're paying for maintenance, operations, those dreaded on-call shifts, and the huge opportunity cost of what your team could have been building instead. Now, let's shift gears entirely away from efficiency and scale, because we need to ask a pretty terrifying rhetorical question. What happens when the AI model is dead wrong, but 100% confident? Traditional software just doesn't behave like this, but AI does. The system genuinely thinks it succeeded, but the output is wildly, dangerously incorrect. That brings us to Pillar 4, high-stakes reliability, where the rule is that the system must fail safely, always. When you're deploying AI in medical, financial, or legal fields, the human stakes are incredibly high. The goal isn't just, hey, it works most of the time. It literally has to be fails safely always. We have to actively anticipate AI-specific failure modes. I'm talking about those silent confidence failures we just touched on, slow statistical distribution shifts, and even intentional adversarial manipulation, like prompt injection. For every single component in a high-stakes system, you have to answer the question, what exactly happens when this breaks? To actually achieve that level of safety, you can use a confidence-gated output pattern. It's brilliant defense in depth. If the AI is over 95% confident, great, we return the result directly. If it's at medium confidence, say 70 to 95%, we still return it, but with heavy caveats and a strong suggestion to verify. But if confidence drops below 70%, the system simply declines to answer, or it escalates straight to a human. This human-in-the-loop checkpoint is absolutely essential. The AI is there to assist, but humans have to make the final call on consequential decisions. Which naturally leads us to another vital question. As we build out these incredibly powerful tools, are we actually designing systems that minimize harm and maintain human agency? This is Pillar 5, designing for ethical AI. Making sure it's fair by construction. We really can't treat ethics as some afterthought that we just awkwardly test for a week before launch. The way we technically implement these ethical safeguards is actually super fascinating. It starts with fairness by design, which basically means using bias-aware data sampling so our models are learning from truly representative data. Then we build accountability architectures. We use model cards to clearly document limitations, and we maintain complete audit trails so we always know exactly why a decision was made. We ensure human agency preservation, meaning users actually have a right to get an explanation and challenge the AI. And finally, we continuously run disparate impact analysis in production to monitor for biased outcomes in real time. It's just a highly pragmatic way to ensure the system is actually working for everyone. All right, our final pillar, number 6, architecting for the future and adapting to relentless change. Look, AI technology is evolving way faster than we can build it, and yeah, that understandably causes a ton of anxiety. Hardware changes, completely new base models drop every single week, the core techniques constantly shift. How do you survive that? By realizing that future-proofing isn't about perfectly guessing the winning model. It's about architecting for change. You need extreme modularity and loose coupling. Treat your models as interchangeable services sitting behind stable APIs and data contracts. Rely on standard interfaces and containers so you remain totally technology agnostic. Essentially, you are building a clever abstraction layer that literally lets you swap out the engine of your AI system while the car is still speeding down the highway. Let's actually look at how this evolutionary architecture plays out in the real world with this timeline. So in this recommendation system back in 2022, they started with batch training on Hadoop. In 2023, instead of burning it all down and rewriting everything, they simply introduced neural models as the primary system, but gracefully kept the legacy system as a reliable fallback. In 2024, they migrated their processing over to Ray for distributed performance. And by 2025, they're incrementally introducing multimodal capabilities. Because they used modular APIs right from the start, this massive, complex evolution happened smoothly over 4 years, without huge downtime and without painful rebuilds. So as we wrap up this explainer, I really want to leave you with one final kind of provocative thought to chew on regarding your own AI deployments. What is your appetite for upfront architectural investment versus chaotic just-in-time scaling? Moving from a flashy prototype to a rock-solid enterprise-grade AI system takes serious discipline, very strict boundaries, and a safety-first mindset. But honestly, doing it right is the absolute only way to build an AI product that is sustainable, ethical, and built to outlast the hype cycle. Thanks so much for joining me on this deep dive, and I'll catch you next time.